to present the necessary tools to define quantum chains, which is indeed the sharp intersection between operator algebras and probability in classical math. Quantum chains have been introduced by Professor Ezekiel in his PhD thesis in 1974, and then it was developed by several authors, and it turns out that it's quite useful in several areas, such as the reversible application of the quantum chain concerns the characterization of the development state of some interesting physical models, as shown by the works by Thomas and Baker. Subsequently, matter chains have been studied by several authors in connection with various applications, including quantum information, numerical physics, and many other theories. In this course, I will try to give necessary tools for students to understand quantum chains, and also several applications and which direction of research. Okay, the first lecture is dedicated to the fundamental ingredient in quantum chains, which is the operator algebra, precisely the framework of the principle of matrix algebra, and then we are going to reformulate the classical matrix chain in this algebraic framework. So we start by defining this is our algebra. This overlap with lectures done by Professor Ezekiel, Professor Wu. So system algebra is an evolutive algebra, an algebra with units, and we have an evolution satisfying these properties. It's a star map. It's conjugate linear, anti-multiplicative, and the norm over this algebra satisfies this identity. The norm of x star x is the same as the norm of x square and the norm of x star square. And the norm of the identity equals 1. Now, the state on a system algebra is simply a positive linear fraction of satisfying these two conditions. First, it maps positive elements into positive real. Like a positive element of a system algebra is an element that can be written in this form, x star x for a certain. And it maps the identity to 1. And now the quantum space is a pair of system algebra A and a state phi. Then you will see that it's exactly the quantum or the mathematical extension of what is in the classical probability space. A replaces the sigma algebra and phi replaces the probability measure, as you will see later. Here we give some examples. In the commutative case, the system algebra can be identified to the commutative system algebra of continuous maps on compact Hausdorff space X for the usual operations, the addition and the multiplication, and here the involution is just the complex conjugate of functions f. And the system norm tells us that it's the supranorm of x of the modulus. And it turns out that this norm satisfies the identity explained here. This identity, that's straightforward. Now, we define also the non-commutative case. The fundamental example of system algebra is given by the matrix algebra. I mean, D by D complex matrix. And define the structure of algebra over a DOC. And then its evolution is indeed the conjugate transpose of a matrix, which satisfies the condition that define the evolution over indeed. And now the system norm turns out that it's the norm associated with the norm operator associated with the Euclidean norm over C. And here it's I formulate this as a nice exercise that can be even suggested to undergraduate students. Here this exercise that shows that the norm indeed for a matrix is the square root of the maximum singular value of A star A, in particular if A is self-adjoint or even like a normal matrix, it coincides with the spectral radius of the matrix. Equivalently, in the finite dimension case, we can consider algebra all bounded operators over a regular space stage whose dimension is D, and then also we have the natural abstraction of system here. And the norm is the one associated with the unit product, the operator norms with the unit product. You can use exchangeably the notation in the matrix in D of T and the D of H in the operator. Now, we define what's a polynomial algebra, which is the star subalgebra of D of H satisfying one of the equivalent conditions. Here I just use a soft version of the definition. Either disclosed with a strong operator topology, or it's satisfied the so-called biconcomitant theorem that states that n coincides biconcomitant on the algebraic image. Typically, the one algebra can be considered in finite dimensions as the direct sum of matrix algebras. Now we find the case of an operator over B over H. The case is indeed the sum of this quantity is related to bases and it doesn't depend on bases. And now we define a really important ingredient for states. So these density matrices are matrices which are positive semi-definite, satisfying the trace of rho equals 1. It's well known that in positive definite matrix can be written in this way for a certain orthogonal basis. Here, as you can see, the lambda I are positive, the sum equals 1, and then it's exactly the same condition that is known for probability measure over finite space. Here it should be just like here. This is the so then we define what's the pure state relatively to its density matrix. Is a state that's given by rank 1 projection. And in general, a mixed state is any state that can be a written convex combination of pure states. And in quantum theory, it's well known that there are more important class of states which are entangled one, which are simply the states which are not mixed. Now we define what's normal state in general von Neumann algebra. Also, I use the soft version of the definition. Indeed, mutually orthogonal projections with phi of the sum is the sum of phi. Infinite dimensional is somehow useless because every state is normal. And we have also this characterization through the correspondence between the states and the density matrices. Every state can be written the trace of the density matrix times. And the arrow is exactly density matrix as we define. Means a positive semi-definite matrix and its trace equals 1. And now we already need to define the quantum analog of the field product of measurable space. Given a finite dimensional Hilbert space H and its algebraic boundary operator B with octanover basis Gi, we define for a given element of B its matrix representation relative to this basis. And we have through this map an identification of B of H and in D of C the matrices of the algebraic matrices of D times D over the complex root. And now for each n we can consider n is a more copy, the n of B, and then we consider the local algebra as it's the finitest product is not the local algebra, it's indeed an without look. And we will see the construction of it's an, the finitest product over n of n. Now, how is it defined, this finitest product? It's defined through tensoring finite, or what is called almost finite sequence, and in the sense that almost all B except finite number are ones. Like if we denote this relation that only finite numbers of Bn are differential, the rest are ones. The second step, I want to clarify this point. For example, if we take the subset I, which is simply 0, 1, 3. This is subset I. And here, if we take an element in the algebra, AI, means that B can be written, the sum of elements of this form. B0, that's what B1, that's the one in the position 2, and here that's for a certain B3. The rest will be 1. One in the position 4, one in the position 5, and so on. Now for people who are not familiar with the transfer product algebra, I will take the simplest case, like when we define MD of C, how is it defined? MD of C tensor on views. Simply, it can be defined through the usual product, weighted product, or a given matrix A, Aij, and B is Dij. times B. It's clear that D square times D square matrix. And then we can generalize to finite number of elements. Now the second step is to define the operations over this algebra. The product is defined on the local algebra. Of course, we all the time take elements almost fine. Means only finite number of Bn are different to 1, to the identity. And now the product is the test product of the product term by term. Means you multiply the Bn by B dash n, position by position. The same for the involution. The test product of Bn star is the test product of Bn star, which is really clear for the product here defined. Here we can see that like A1 tensor B1 times A2, this can be easily checked, times B2 is A1, A2 tensor B1. The same for the involution, the conjugate transpose of A tensor B is the conjugate transpose of A tensor the conjugate transpose. Then these operations are well defined on this local algebra. And then we define the impedance Gn for a given B in the simple algebra B. We just put it in the nth position. Means we take B on the nth position, the rest are on. For example, if we take G2 or G2 of a certain B is 1 on the position, the first position, 0, tensor 1 on the second one, means position 1, tensor B, and the rest should be 1. And so on. Now, for the norm, the same for the norm here, the norm of the tensor product of Bn is the product of the norms over, of course, the Bn should be almost, almost all of them equals 1. And then the mass Gn defined by 4, like this formula defined before. Are not the learning, of course, because since the norm of the identity equals 1, then the norm of this quantity is the same as the norm of the first children that we consider. The norm of G2 of B is the same as the norm of B, because the norm of 1 equals 1 for the system. And the system algebra, which is the quasi-local algebra, is defined as the system closure of this algebra. Turns out that it's an algebra, it's star algebra through the defined operations, and then it has a system closure, which is the system dash product of the system Bn of algebra. And for any region, we can define the system subalgebra related to this region, which is generated by the algebra AK A9. And it turns out that in our case, it's easy model to the tensor of cardinality of hypothesis of the fields. It's also the algebra generated by the embedded decay of DK. pursues the notation, the very specification. B of which tensor and times. And here since H is finite dimensional, we can see that this impulse is morphed to the alpha button operator over the tensor product of n copies of the infinite space H. And this is very useful to define some classes of quantum chains and to do computation, because it allows to use both the algebraic picture and the Schrödinger picture. Now we define the shift over the local algebra that shifts the elements. Means the shift of an element A, tensor A1 is indeed A, we just put 1 in the first position and we shift the rest, because this is an isomorphism defined on the local algebra. Indeed, it maps the local algebra indexed by n to the local algebra indexed by n minus 0. For a clear representation of quasi-local algebra, people are interested can see the book by Professor Volume 1, a freelance theory of quasi-local algebra for general unit sets. Now we are ready to define the notion of quantum stochastic process. Or generally, we can say also algebraic stochastic process if we don't have the topology without knowing on star algebra. And when it's when we topology, we say quantum stochastic. An algebraic quantum stochastic process is equivalent of an algebra A, state phi, and a sequence of sample algebra Pn, and also a sequence of embedded Gn. Here we have like the construction of all of these. Here in our case, indeed A is in our case A is the quasi-local algebra. Here An, which is the tensor product of Bn or Bn, or related to Gn here. The process is known as algebraically homogeneous if all the simple algebra Bn are copies of a single algebra, if they are all copies of a single algebra. Means star is more to a single algebra. Now for the homogeneous infinite tensor product, we may identify in the finite dimensional case the algebra A to the infinite tensor product of NDOC. And the state phi is of course locally normal, because what we mean by economic is that when we take a finite subset of n, so phi can be written in the place of a certain density matrix. Since here, if we take a finite gradient of n, then this tensor product over I and DOC is finite dimensional. To A and DOC, and so by the end of I quotes, then it's finite dimensional, then phi is the restriction of phi. times of ordinary positions, then it appears on the hand position. Now we are ready to reformulate the usual theory of marked chains in this algebraic mode. Now it's known that marked chains are processes that are characterized by the fact that given the future that depends only on the present, if we have the information on the present of past. But it can be also reformulated using conditional expectations. So something defining the notion of conditional expectation. In the classical case, indeed the conditional expectation is a projection from a measurable space omega P into a sub-measurable space. L1 space into a sub-measurable space by changing the sigma algebra F by the sub-sigma algebra G. And the conditional expectation of the random variable X given the sub-algebra G is indeed the new random variable is denoted by E of X given G, which is G measurable and satisfying this condition. It's integral over a subset of, an element of the sigma algebra. G is exactly the integral of this. The expectation of E of X given G satisfying this condition. And what is really important in that condition expectation can be considered in an algebraic approach, since it's a linear map. Indeed, it's a projection, as you will see. It satisfies the linearity. And it's also projective, since like the conditional expectation given subalgebra, then another subalgebra H, it gives exactly the conditional expectation of X given the last one, the smallest one H. And it satisfies this quite important condition. Means if V is a G measurable random variable, then the conditional expectation of Zx given G is the same as Z times the conditional expectation of X given the sigma algebra. Now we can reformulate the definition of marked chain using conditional expectations. The usual marked chain. Xn is the sequence of random variable built in S. It is, it's just a sequence of random variables. And then we consider the filtration, the backward filtration. And then here Fnx is the sigma generated by the first n plus 1 terms of the sequence. The sigma represented by x0, x1, xn. And then we set the mark property. Define the marked chain. The probability of xn plus 1 belonging to set B, given the sigma algebra generated by, the past projective sigma algebra generated by x0 to xn, is the same as the probability of xn plus 1 in B given xn. In the discrete case, like we say, it's also convenient to say that E of xn plus 1 equals G given xn plus I, and xn minus 1 equals certain in minus 1 till x naught equals I naught is the same as the probability of xn plus 1 equals J given xn. And now we have this equivalent reformulation for any measurable function. We have E of f of xn plus 1 given the sigma algebra Fn till n is the same of E of f of xn plus 1 in a given x. Then we have this characterization of marked chains. It's given by, the distribution of a string is given by the initial distribution of the first term, its node, and the sequence of prediction kernels, defining the transition from the state to time to time plus one, and also in a more simple way, you can define the distribution of the microchip through a sequence of transition matrix. Like the sequence of transition matrix is here, you can iterate is simply the probability of xn plus 1 equals j given xn equals I. And in the homogeneous case, this transition does not depend on it. In the homogeneous case, we have this transition, so the n steps are indeed the power n of a single stochastic matrix. Here, the stochastic matrices are matrices we call positive entries, where the sum over each line equals so. Now, I just give an illustrative simple example of the two-state part chain. Here, in general, we have the transition matrix at time n is characterized by a pair alpha n and beta n, and we can see that alpha n are pointing at the sum over each line is 1, and this, of course, is useful. Mathematical chains have a lot of applications in several fields. Here, for example, it can be useful for pattern operational markets, or converting the origin switching probability. And in the homogeneous case, also, we have the transition probability independent of n. I see this is very elementary, but I think it's really important to state this grammatical, because you have two frameworks, the probability one and the other one. Now, through this important theorem, this in the literature in several versions of kind of theorem that looks to represent any probability measure using state. Indeed, if we have a compact algebra space S, and the D of S is four-dimensional algebra, which is generated by open sets, there is a one-to-one correspondence between probability measures on S, B of S, and states over the star or the C of S. Before, you remember that you have seen the star algebra structure of this. Then we have this correspondence between probability measures on S and states over C of S. And here is the first way to define the state relative to the measure. Phi mu of F is the expression value of it related to the measure mu. And also conversely, you can define for every given E, phi mu of E is indeed phi of the projection on E. The projection on E when we consider elements of the basis. I will detail this here. As you can see, like C of S, let's take S is 1, 2 till D. And then C of S can be identified with, algebra of the angular matrix. Yes, for QP46, we can associate the diagonal algebra defined by f of 1, f of 2, till f of t on the diagonal. So that this map is a star isomorphic, like it's obvious. And then we can define, you have probability measure, like each probability measure on S is defined through you have the given state. And if it's, let's take an something of S. And then we consider in the vector space notation of the projection EII, and E can be considered to be like, if you consider the projection EII, diagonal matrices and you are 0 except the I position is 1 and the rest is 0. Then we can see that the E is considered to be like this sum, the matrices, where once the appear only on the then the mirror, if we consider also this matrix, we have a mirror which is identified to this polarity line, mu of 1 of the vector, mu of D. We can consider also the density matrix, rho mu, which is the diagonal matrix whose entries are the elements of mu. And now we can see that the mu of E of the F is exactly the trace of rho, and here we can consider take this P of over E or over C. Here for I in E. Then it becomes the trace of rho mu times P becomes a state. So over here, and this state can be extended to general function from S to this is exactly phi of P. But you can see that this one is P. Okay. Then we have this Ibadan change. And for the theorem, for several versions of the theorem, people are interested can be transferred by books. For the functionalized approach by Conway, and also for the measure theory approach by Witten. And here I just recommend the proof of the book theorem as a small exercise. Step by step, I define U, phi from U and the V. And now we arrive to like dictionary that the analog to classical and framework for text. I mean, for general for like for finite space, we have the simple space S is like replaced by system algebra, which is in this case C of S, and also it can be generalized into C. And the infinite tensor product, I mean, the measure product is replaced by infinite tensor product in matrix algebras. And for an atomic theorem, we consider the minimal production is written here in the direct equation of the same as the one I defined before here. And is replaced by the state or generalized state. The expectation value is the trace here, phi of A, phi mu of A, this of rho mu times A. And then we need the conditional expectation for further extension of the notion of not K. It turns out that the conditional expectation can be replaced by or generalized into quantum conditional expectation, since they are like defined as projection on spaces, linear spaces. Then we can see that it's this should extend then to with the algebraic framework of system logics, fundamental. In addition, there are many extensions, of course. Some of them are convenient to define like chains, some of them not. For quantum conditional expectations, one example is suggested by Magaki, which is an exact translation of the classical notion into the framework of one-line algebras. And it's defined through these properties, which are, as you can see, they are similar to the ones stated on the classical case. They are positive maps, and we satisfy this condition as we have seen it in the classical case, like E of B A is B of A, or B in B and okay. And it presumes the identity, maps the identity of A into the pregnancy, which is the same of its subalgebra B. And it satisfies this condition. And it turns out that there is a characterization of this map. I mean, here by the work of Yamagaki, where he introduced the notion of conditional expectation in operator algebra. Then there is another work by Jumiyama that characterizes these maps to be normal operations. Here there is equivalence between these two assertions. E is a Yamagaki conditional expectation, and E is a projection of normal operation. And then for people are interested in the book, I see the book by Sakai, where this book is detailed. Now, the question, which is quite important, is this type of conditional expectation convenient to define what conditions are not? It turns out that in the works by Professor turned out that this extension is not convenient to define a quantum chain on the general the use of this type of conditional expectation lead to a trivial class of conditional Markov chains in the normal case. Indeed, according to this exercise, if the state file on this tensor product algebra is compatible with a Yamagaki conditional expectation, then this state should be product state. And the product state in the quantum case means the independence of the first, means that it's exactly the analog of the independent random variables. Each one is two independent. The same that the distribution is given by the state phi is the tensor product of the first random, like the distribution and the second distribution. And it's well known that the independent sequence for random variable is a very, very marginal, trivial marginal chain. Therefore, extension are needed to define. Here it is specified. Let's for the next picture, if you can prove it, if you have enough time. And it turns out that more convenient extension of the notion of conditional expectation in the quantum framework is necessary to be able to define a satisfactory extension of quantum function. This what was done by Professor Ezekiel by introducing what is called quasi-function. Before we need to define what's a completely positive map, which is a map from system algebra A to B, for which these maps are positive for every. The matrices, positive matrices are elements of, defined over M of A is positive for every. And there is another simple characterization of positive maps that states that the sum, I will just write the characterization set away. The sum over ij of ai, bi KJ, DJ is positive for every n, and for every table, AI, I, and 1 and n, in the algebra A, the same for B. Which is exactly the formulation of the fact that this man, why he is positive. Those other completely positive marks can be represented in what is called in the literature culture presentation. That the phi can be written through this formula, the sum of the certain zi star a b. And this representation is really important in the framework of quantum information because there is another representation of what is called quantum channels. We will see later its connection with Markov operators defined in the sense of quasi-condition. Now, the position expectation is defined to be a unit of Markov from star algebra A into the substar algebra B that satisfies the complete positivity condition and preserve interaction. Often we take CPIP to refer to complete positivity preserved marks. Now, I will reach with the definition of quasi-condition expectation. Given the triple here, it's still like there is an additional ingredient here. We define quasi-condition expectation related to a triple C A of P algebras. Next triples, star algebras, quasi-condition expectation from A to E related to C is a completely positive mark A, E from A to B, satisfying this condition. As you can see, this closure condition is satisfied both by the usual classical condition expectation, E of CA is C E of A, and also by the Umagati condition, which by the difference between the Umagati condition expectation and here is that this one is satisfied for B, as you can see here, for the Umagati condition expectation. This property is defined for element B of the algebra. There is no C. The third algebra is absent. That's why this leads to triple state, which is as perfect. Now we have this property for relative to the smallest subalgebra C. And then we have the Markov property defined through this equation, like E of C dash, which is the complement of C, intersect A is included in the complement of C intersect. Even the Markov property is defined relative to the subalgebra C. Now we will see why this corresponds exactly to a satisfactory extension of Markov chain. If we are given a triple of algebra, like the past algebra, if you remember the relation that we considered in the infinite product of algebra, here the past algebra is indeed the algebra A 0 to n minus. And the present algebra is AN. Let's use the same notation here. Let's make it clear. If we take, or maybe, yeah, it's good. Okay. Now we are given three algebras. The first one, which is C here, here is C, the smallest one, and the first product of the past algebra and the present algebra, which is here B, and the biggest algebra A, past, then super, present, then future, which is A. Now, a Markov quasi-condition expectation can be identified into a map that is E equals to the identity over the path algebra tends to E. Of course, when these algebra like are vulnerable factors. In the most important case, we have this notation. A0 to n is the algebra that has present AK means AK is a copy of MDOC. It's clear that we have the past algebra, exactly the same notation as the past one. The past algebra here is A0 to n minus 1, and the present algebra is A to n. The past algebra is A past is here A0 to n minus 1. And A present is A n, which is a copy of MDOC, and A future is A n plus 1. And here the bigger algebra is A0 to n plus 1. Now for the macro property, since the component of this algebra is, since all of the algebras are factors, here we can see that the center of MDOC is reduced to the identity of 2 plus 4. Then the component of this algebra, of course, in the biggest algebra, which is the fantastic product, then it's exactly A n plus 1 to the, I mean, here n minus 1. Then it's the algebra from n to k. And if we apply this macro property, this one. We have the component of C intersects the algebra A. Intersect the algebra A, which is it becomes A and intersect A0 left. So it gives this algebra A n plus 1. It is exactly the algebra in which the transition expectation defined here is acting. This transition is the n is acting on this algebra A n plus 1, and maps this algebra into A n. Now, instead of using the sequence of quasi-transition expectations, we have to use the sequence of transition expectation, since we have equivalent representation in the case of FNMS, that's a product of full matrix order. Now, using this transition expectation, we can define two macro operators, the backward one and the forward one. Forward one is defined to be E of x tends to 1 on the second component, B, and the backward one is E of 1 plus 1. Now, these are macro operators that are literally derived from E. And a important question concerns the reconstruction of E given the two macro operators, the backward and the forward. Is it possible to reconstruct E? Because it's somehow exactly similar to the reconstruction of the joint distribution of two random variables given the manual distribution. You see, like we have the depends on the correlation to run very to have row X. It's not that analog, but I just want to make it clear in the renders. And the row Y, how can we construct the long distribution XY? The simplest case is when we take row X plus row Y. So that in this case we have the independence, which is treated if we consider the homogeneous condition expectation as extension. So it's true. Now, if we have correlation between X and Y, is it possible to reconstruct the joint distribution? Let's put here in the usual copy notation Ux and Y. Is it possible to reconstruct Uxy given Ux and Y? It's done on the random or the correlation between X and Y. Here they say, not exactly the same, but just to show that even if the quantity is there is the notion of random, but what's the connection between the forward and the report, and it's possible to reconstruct it using it. It gives a little idea about the quantum randomness that is present here and it depends on it. Okay, so now we define the whole conditional density matrix. The conditional density matrix is a operator K satisfying the stage over the second component of K star K. This is really useful to produce many examples of quantum chains in connection with several like Pauli matrices, spin models, and also of the quantum box, and these have been done in many papers in the literature, both in the one-dimensional case and countries. Now we are ready to define quantum mechanics. The sequence of states finite is said to be predicted here, exactly the analog of the notion of sequence of predictive measure in the sense of Kolmogorov theorem. Now the sequence of states over the local algebras is predicted if the section of the state by n plus 1 that's defined on a0 plus 1 to the subalgebra a0n one side unified. And this predictive condition is important in defining many classes of particular chains in connection with phase transitions and other phenomena or spin models, as you will see in the last lecture. Now we are going to set the definition of quantum chains as introduced by Professor Ezekiel in 1974. So a quantum chain is defined to be a quadruple of algebra AN, which are here the observation algebra, the sample algebras, states by zero on the initial algebra is replace the initial states, the initial distribution, and a sequence of transition expectation. And in addition to that, we may add, depending on whether these transition expectations present the advantage or not, we may add a sequence of boundary condition. Now, there is the state algebra with 1. We have an initial state replacing the distribution of the, like, let's say this is the analog of mu x0, the distribution of the first term of the chain, and En is a transition expectation from An plus 1 into An is exactly the analog of the transition kernel or even the transition matrix P and Ij. Remember the transition matrix, let us go. And also the boundary condition is additional, given in some examples of the classical Markov chain, such as the one associated with the Ising model. We have this boundary condition present, but it's it's more significant in the quantum case, maybe with on trees, for example, it leads to phase transitions. Now, the matter chain is the state phi. Let's characterize it through these ingredients. So it's the state over the infinitense of product algebra. It satisfies these correlations. Phi of the finite, like the finite password, is characterized by this equation. Is the final root of the first transition A root. Then E1, we have this equation, and the last term is the bottom. Now, this equation, if, like one of the most classical results, states that if we have this, if like we define this restriction, if we need phi n, let's say this, if it's phi n, like phi n is the restriction of phi over algebra A. One of the methods to reconstruct phi something from this sequence of states is what defines the root as the projected sequence of states is when we have this transition expectation satisfy this condition. If E of, let's say, En of 1 in the position M, that's all. The bounded condition in the position n plus 1 equals to Hn. Then the sequence is projective. Then phi n is a projective sequence. Means phi n plus 1 with respect to the algebra A. The n coincided with phi. And then this sequence is projected using the quantum analog of the Kolmogorov extension theorem. There is the unit state on the infinitense product algebra that satisfies the restriction over the local algebra is over n plus x. And we call this sequence as it's defined, the root is known to be projective sequence of states. It means any projective sequence of states, maybe these correlations lead to the quantum functions. Also, in the homogeneous case, the homogeneous case here is characterized by the fact that the transitions are the same, like En are the same, doesn't depend on n. We have this simple formula, like the finite correlations of phi are defined through this expectation, which is exactly the analog of the extension of the measure. Like when we have probability classical math chain, we have the measure of the chain over the n. The n first steps is given by an analog formula using the transition. Now we arrive to an important embedding of classical math chains into the quantum framework, and this is what has been done by Professor Ayoola, and to show in a very clear way how classical math chain can be embedded into the quantum framework using this map, as I said before, and then we using this condition that's K is indeed the sum of this bracket and answer KH, where KH is the diagonal matrix whose matrices are the square roots of the transition matrix. I mean, in one case, P here is transition expectation is defined in a rigorous way using the trace-forward technical method. And then using the same formula here, defined using this formula, this one, for this specific transition expectation, I'll define what I put this for you. This one, or this additional density. K, we get exactly, if we apply to the projections, to the atomic projections, we get exactly the classical probability for the first n particles of the matter. Exactly the same formula, which is indeed U is 0 of either times P I0 I1 till P I n minus 1 I n, where P is the transition. Here, this paper is really recommended for people who are interested in starting understanding quantum chains, namely if they have a background in transformation. This is a very nice way to see that mathematical chain and classical mathematical chains into the quantum frame. Okay, maybe I should stop here and I let the question, question.
Okay. Can you hear me?
Are there any questions?
Can you hear me? So please let's give Professor Susi a round of applause. I guess for so, I thank you so much for the method you have adopted. Now it is time for questions. If you have anybody to ask questions, I have very many. I shouldn't be the only one that should ask questions. So I want questions. Please come over. Okay?
Actually, I cannot hear you well. The same problem happened.
Okay, like this. Can you hear me now?
Because there is an echo.
Yes, echo.
There is an echo. So it's not easy to hear.
Mute down. Better? Is it better?
Actually, not really. I can hear, but it's echo. I cannot hear well.
Can you hear me like this? Is the audio better now?
Maybe that's possible.
Hello? Can you hear me better now?
Better to write them in the chat because the voice is not that clear.
Okay.
Ask your question, I'll write.
Good afternoon, Prof. And thanks for your wonderful presentation. At the beginning of the lecture, you defined what a quantum stochastic process is. We have classical stochastic process, just like we have classical metrics and quantum metrics. And if yes, is it the same thing as a chaotic system in physics?
You mean about applications in physics, yes?
Hello?
The question was about applications of this process in physics, yes?
Yes,
I understand.
All right. At the beginning of the lecture, you define what a quantum stochastic process is. In physics, we have quantum metrics and classical metrics. So in mathematics,
works in this direction. The Poisson stochastic, the quantum process, yes? And I think some of the works have been done by Professor Ezekiel in this direction. There are some nice work on the
questions are being typed on the chat. Please look out for it. Some questions are being typed on the chat. Please look out for it.
Thank you, Bro. Yes, I want to ask this question. The last statement about embedding classical Markov chain, quantum Markov chain. Yes, at what points can we apply quantum Markov chains? Application of quantum Markov chains. The second question is, at what points can we call quantum Markov chains quantum Markov states?
Yeah, that's a really nice question. Concerning the quantum Markov fields, yes? Is the question concerning quantum Markov field, yes?
Did you get the question?
I think there is a question concerning Markov field, yes?
I'm not clear whether you get the question, the last question. At what point
The last
do you,
question.
at what point do you call
in the chat, yes? I mean, the last question is written on the chat, yes?
no, the one that was asked using the mic. Please repeat your question. Listen, please.
Yes, the last slide talked about embedding classical Markov chains in quantum Markov chains. So the question is, where can we apply these quantum Markov chains? Then the second question is talking about, yes, at what points can we call quantum Markov chain quantum Markov states?
Yes, that's a nice question. For the quantum Markov state is a subclass of quantum Markov chains that is compatible with the, it's fully described in this class. I mean, it's shown that by some works by Professor Ezekiel and many authors, including Fidario and also Orly, and many authors, Fregerio also, the one in the paper where he introduced the notion of quantum Markov states in connection with the Markov cycles. And then, after these states was proven to be diagonal, and also the structure is fully described. And it's important component. Given that the information flow of this class was investigated in many important papers with the non-tropy and not a lot of stuff has been done in this direction. Even the extension to trees have been done. Both in for the one dimension case, these states have been investigated in the bosonic case, the Fermi case, and I think it's an important subclass, but also chains, quantum Markov chains, which are not states, are also important, including the one that we will see in the next lecture. And if I hear well, the second question concerns the Markov field. Quantum Markov field. Quantum Markov field is a bit correct, but aim to extend the notion of Markov field to the quantum frame. Till now, it's one of the most important of the questions because some people they tried, including Professor Ezekiel and myself and some other authors, and it's still an open problem for general graphs to define quantum Markov field on the general, but there are some ways. I received the question: is the quantum stochastic processes the same as chaotic processes in physics? Actually, I not really know about chaotic processes, but for the quantum stochastic process, they are maybe more mathematical objects. They have many applications, yes, but It depends on the approach. Consider in physics which fails, because there are some communities using several notions. But I will see if it's equivalent or not. Are there other questions?
Yes, there are several questions. One of them is that in equation 7, what topology are you using? Look at the slide, equation 7. What topology is employed there? Second question.
The sequence of matrices or topology convergence.
No, the type of topology, strong, weak, or equation 7.
Yes. Yes, for the quantum matrices, what's basically the topology, the weak star topology.
Second question.
The weak star topology. Yes. The question is. Is that the question about the topology that used the convergence for matrices? Yes.
Yeah, just to emphasize more on the kind of topology which you are using. That is the question. The second question is, what is the meaning of diagonal elements that we expressed around the last slide? Of diagonal elements.
Yes, about diagonal elements, yes. Yeah, that is the elements which are important. So the topology on the full system, which is the classical product of matrix algebra, in the convergence of the sequence phi and things, we use the weak star topology. Which defines the version coincide with the usual norm topology. That's the topology of pointwise convergence. We don't use a lot of topology in this context because the productivity is often shown to be most of the cases we get the limit is the strongly finite size. Meaning the sequence becomes stationary for a given element state.
Okay. Another question is, can you express examples of the quantum Markov chains in terms of the body examples of quantum Markov chains using the spin model or the Pauli matrices? Can you construct examples?
Yes, that's what
we'd love to see.
Yeah, that's a good example.
Yeah, we'd love to see some of these examples.
Yes, we will see in the next lecture.
Okay.
Concrete examples.
Okay, then
Of
go to page 58 of your slide. Page 58. Page 58 of the slide. Page 58 of your slide.
the one.
Page 58. Page 58. Go back.
Which page?
58. Yeah, yes. So go back. 58. No. Yes, go back. Okay. No, page 58. 58. The last line on that page. Go down.
For this?
Yes.
This one.
Yes. Your KH defined as the diagonal. What do you mean by PH1, PH2, PH3?
I didn't hear you. I'm sorry, but KH is a diagonal, yes.
Yes, the meaning of your PH1 to PH3.
Why the difference on H?
The meaning.
You see here, you take simply the line H of the capacity and you put KH. You see? Because as you see here, this KH is a diagonal matrix associated with the lineage of the classical stochastic matrix that defines the Markov chain. I hope this is clear.
Yes, it is clear. Thank you very much.
Thank you.
Question more.
Thank you, Professor. Yeah, on one of the slides, you talked about relative expectation as postulated by Omegaki. Same Omegaki postulated the idea of relative entropy in quantum communication theory, quantum information theory. So I want to ask, is there a connection between the relative expectation and relative entropy?
Yes, that's the question.
Is there a relation? Okay, is there a relation between relative entropy and the conditional expectation by Omegaki?
About the connection of that with verificator, yes.
Did you hear the question?
Clearly, that it's a very challenging to hear because using the mic, we like use an echo. But if you use the phone directly, maybe it can be clear. The question, like using the mic on the phone. Maybe.
Is there a relation between the relative entropy in quantum communication and the conditional expectation by omega t? He defined both. The questioner is asking if there is a relation between the two.
Maybe even like typing it on the chat.
Okay, Shai? Yes, just a minute. Am I right with the question? Check the chat. Maybe we are not typing the question.
Okay, because if there is a relative entropy of quantum communication and the conditional expectations, we find them. And that's a really nice question. That's a really nice question. It is, there is a really nice book written by Professor Oya, and it's about quantum ontology use, in which you can find, I guess, satisfactory reference to this. About even because there are entropy, several measures of entanglement. They are being introduced by a really wonderful Japanese team. Like, some of the notions were introduced by Yamagaki himself. Then Araki, Oya, and lots of people. And there is a huge number of organizations and such. So yes, there is a one. But this requires maybe read more about, because as I said, many pages and also books going in this direction.
You get what he said. He referred to some other authors. He referred to some other authors. And they are what you think. I can also see different.
Okay, so well, Susie, thank you so much. Please let's give a round of applause.
And the condition expectation, mechanical condition expectation. I just want to recall you that historically it was Umegaki who first introduced in the theory of sister algebra also the notion of relative entropy. And at that time almost nobody was speaking of quantum information. The student of Umegaki was Professor Ayoola, and we collaborated and we went on and we founded this, the first journal of quantum information, which is called the Open System and Information Dynamics. So it's just an historical remark.
Thank you very much. You can see Professor Agadi is one that started so many things in the field of quantum probability. So you are lucky to be meeting him and to know him personally. Please let's give him a round of applause.
When we study a particular class of mathematical chains, known as integer chains. I think there is like some physics training in this school, so I mean, it's familiar with the ones who are important on quantum mechanics with the notion of Higgs, which is like one of the most important notions in quantum dynamics, like quantum phenomena. This particular class of quantum chains present a really important application of quantum physics in connection with the notion of quantum things. So, the segment things have been introduced by Professor Ezekiel and Professor Ezekiel in their work in 2005. Then, in a series of papers, Professor Ezekiel with Professor Matsuyoka Oya, they produced a number of papers that show the implication of quantum chains on quantum dynamics. I don't know. Someone? Is there a question?
No question.
Okay. These class of quantum chains have been shown to be really insane. Like, in a series of papers by Professor Ezekiel Olusola Ayoola, and there are a lot of applications within the quantum dynamics, such as reciprocals on a entanglement model, or concrete examples such as the case of a paper and box in its quantum one possibility community. Now, if we have this this completely positive map, let us find that it's not preserving here one different one. Then we call it a single matrix. It's completely positive, but not preserving. Now we try to define condition expectation based on this integral matrix. Such that the matrix operator is the backward, the integral matrix operator is the backward matrix operator for this condition expectation. Now we define this map for it is like the linear extension of this map. They show that to the test product of AB, we associate the subalgebra. Extracting the matrix on A tensor B to be the matrix Aij, Bij. It can be shown to be completely positive, and then we define the transition expectation to be the composition of this map N, and the identity on the first component tensor the integral multiple operator on the second. Now, if we can see like E of and E of 1, E of 1, that's certain A is the shoe product. Or let's say here by 1 we conjugate the matrix which if all entries are equals. So it becomes the test product of 1. That's M. Okay? So if we take the identity, then all entries are 1, so it leads to 5. Okay. The fourth one is the backward. We can see that here it doesn't be preserving, but 5, the backward microoperator associated, is not preserved. And this is the idea behind the integral matrices. So integral matrices are simply the matrix chain as we defined before in the first lecture, for which the transition expectation is the one associated with the single matrix. These chains are known as integral matrix chains. Now we provide another perspective to define this chain using the Schrodinger picture. We use the action on the Hilbert space H. We simply consider a classical Markov chain, and this suggests the initial state P and the transition matrix capital P. Here we take the space. And then we define this state vector. Psi n using the tensor of the base H. Psi n is the vector that belongs to the tensor power H. Tensor power of the Hilbert space H. So here psi is the vector here, and our main problem is to find the limit space that can be interpreted as the limit of the expected value of A on the unit vector side. Here we can show that psi is the unit vector, like considering the norm and the fact that phi is interpreted as the limit, and then you see here, and then goes to infinity. This reverse spin can be bigger again, and then we interpret this state as the limiting variable operator A, and here we can say taking the local algebra is going to be more convenient, A and log is A is finite. Then we extend this by the following look. Here we define the state phi n to be this state. Phi n of A is the expected value of A plus x on the side on the vector side. And you want to construct the sequence phi, the limiting state phi using this sequence. But we should also investigate the correlation of this. We define its density matrix as here the phrase on the n+1 factor, because as you can see here, if we have the state of an, if you write psi A psi in a certain reverse space, this can be interpreted as the trace of the bracket psi times A. And with this notation one, we may use the partial trace, because the trace on the partial trace is the same. Like here, the density matrix becomes the trace of, in this case, phi n of A is indeed the trace of phi n plus 1, psi n plus 1 times A tensor 1 in the component n plus 1. But here we can also write, because this vector belongs to the algebra B1 0 n plus 1, or here also n plus 1. And this vector belongs to the algebra. To have the compatible notation, we use the phrase of the partial trace over n plus 1 of the algebra partial trace with the homotech condition, then we get the psi n plus 1, psi n plus 1 times A. Then we know that the density matrix of this state phi n is this one, is the partial trace over. And here we detail this density matrix in terms of elements of the basis. And we can see that we can express it using these brackets. And it's clear that it belongs to the algebra A0, because this one is the first factor, 0 to n. Historically, and given market case, as it was introduced by Professor Ezekiel and Professor Ezekiel Olusola, it was like an extension of the classical notion of randomness. But then the result is already one called class of conformations. And then we can even express the complete positivity of the transition expectation in a clear way, using a sequence of partial results. Even in the homogeneous case, we can consider this sequence of partial results where U is an isometric matrix. The subtle point is that when we consider something U, then the matrix whose entries are the modulus of Uij is stochastic. And then we get the square root. But entangled motion expectation on, if we have a vector extending dn, the algebra, and then x plus 1 in n plus 1 algebra, then the action of dn can be explicitly in terms of the isomorphism this way. By this notation, if then ij, we mean the n plus, the entries ij of the same, for example. And it's clear that it maps Pn plus 1 into, it maps like Pn of Pn, so Pn plus 1 is below included in Pn. Now, to do this map, we can also consider the simplistic case for which we have E of k equals to E is simply the real square root of k and k. But these two constructions, we have the same statistical properties where we can take any complex square root or the real one, and there is no big difference. Then E is a conditional, and then we have these correlations for mark k, which is a chain of things. Now, these Markov chains, according to this theorem, they have like exposed in zero references, including the first work by Professor Ezekiel and Professor Ezekiel Olusola Ayoola. It was shown that this limiting state phi is indeed interpreted as the limit of this sequence of continuing states. This is, or can be interpreted as the limit of this state with E in the integral knowledge. This is very important point, and that allows to interpret the integral Markov chains as the limits of this expression value as n of the vector psi m a by n. You will see in the presentation of the conference that this has a very, very important implication in the one-dimensional University system. Now here, if we consider an element f of the diagonal subalgebra, we can see that this condition satisfies a very important property to what is called the digit preserving conditional expectation. And this digit preserving indeed was studied by Professor Olusola. It's the same paper in which we consider that the building of the classical Markov chains into the quantum trade-off. Because he considered also the classical counterparts of, the classical representation of quantum Markov chains. This property is satisfied by these entangled motions. It is like, it's satisfied that E of, if we have F diagonal and G diagonal, then E of extension is also diagonal. There's other in this area. And then, using this approach, we can also interpret the classical Markov chains from the entangled ones. It's another way to get a bridge between quantum and classical Markov chains, and then it gives a real sense of entanglement, because entanglement concerns the non-commutative parts. And here, 2 S of pi minus the trace of the density in x of pi times the log of so you can see that for the pure state, you remember what's the pure state? Like here I want to just illustrate it with this point because you know that the rho pi indeed can be written as sum of lambda I times the bracket I, because it's positive. And where the lambda I are positive, and the sum equals 1. So the sum, we can see here in this case that the polynomial of pi is indeed minus the sum of lambda I log of lambda I. Which portrays exactly the Shannon entropy of this probability measure. Mu is lambda 1 lambda 2 lambda. Now, why this measure, which is the mononomial entropy, is used when we are studying pure state? Because you know, pure state is simply the state having this form. And it's I call psi psi. Psi is the person. Then, if we try to do this decomposition for rho, we get lambda 1 is 1, the rest are 0. Therefore, when we compute the mononomial, we get 0. Because only 1 equals 1 to the rest. And then the mononomial entropy is useless as a measure of integrity for like pure state. Yeah, it's used. Indeed, it characterizes whether the state is in this one. If the mononomial entropy equals 0, then the state is pure. If it's strictly positive, then it's zero. Then you can do all this. But if you want to have more information about the integral structure of pure states, mononomial entropy is used. There are also some other methods, such as the quantum useful information for a bipartite system. You have our sense collector system. Then we can see the mutual information of phi 1 and phi 2. And here, in this separate case, this characterizes whether the state phi is a product state or not. Here we have phi is a state on the algebra A1 plus A2. Phi 1 is, or phi I is the rejection of phi on the subalgebra X is the rejection of phi is the subalgebra AI. So it's fine. And then in the simplest case, or in the current case, we have if phi if indeed phi is the potential product, if phi is phi 1 plus phi 2, then the condition, the quantum mutual entropy of phi 1 and phi 2 given phi is positive. So this will be the class product of rho 1 and rho 2. So the difference between the same and the same. Indeed, it's enough to say that here, this is equivalent to say that rho phi is reflects whether the state is a product state. If it's a product state, then the quantitative entropy vanishes. Also, we can define the quantum relative entropy. There were a question in the first lecture concerning the quantum relative entropy. For a state phi and theta, we define the relative entropy of phi given theta as rates of rho phi from rho phi minus rho phi. It is in geometry theory. As you can see, it's like the particular case. It's the relative entropy of phi given the test product of phi and phi 2. Now we are ready to define one of the most important phases of entanglement, which is known as the degree of entanglement, introduced by Professor Oya, and then studied several years. For theta in B of H transfer H is acting on the H in the complex system. Then, and then we take rho is the partial traits of the phase. First component, and the sigma is the first trace of this classification to be precise with the classification. So both of them are classifications. I mean, they are known to be the marginal. As for the distribution of the couple, we have the marginal distribution. This is but here we know. Now we define the quantitative information as was before on the restriction to the first system and to the second system. Rho, S, the direct. Now we define the degree of entanglement as using the degree of the volume of phi and of the sigma minus the default approach. And then for a state defined on like here is the degree of two relative to rho and sigma. For the multi-part system, we define over all the conditions of the system. So we are still in the system is depending over rho sigma of the degree of entanglement of the given rho sigma. I mean, for the multi-part case, we have more than two atoms. We have many. Here is a nice exercise that show the difference between classical and quantum systems. Here, if we compute, one may ask the next question, if we compute the degree of entanglement of a classical probability space, means for diagonal rho and zero, for diagonal this matrices. Here we can show that the degree of entanglement vanishes. This means that the degree of entanglement is purely quantum. And unlike the variable, because we have seen that the variable when the measure is diagonal, I mean the matrix is diagonal, it coincides with the union of Shannon control, which is a notion in the classical probability. Here the degree of entanglement is purely quantum, simply because it vanishes when it's a diagonal or a classical state. Okay. Now we will try to characterize the chain of pure states. Here we have the theta in the pure state as we So are studying state on a definite system, we may define the asymptotic degree of continuum of the state phi as the limiting the degree of continuum or the limit of the degree of continuum of let's look this. Here, as we define before psi n is the superposition state given by the formula for this here. So say sample A0, I1 with n of the square root of the I0, square root of the I0 I1 to the square root of the IN minus 1 IN times this vector I0 times 1 I1 0 it's a superposition state of this product. Now the degree of continuum of the Tiedemann chain is distant. So instead of think of finding the opinion of this state acting on multiple places. You saw in the work by Professor Ayoola and Oya, they find that this quantity is not easy at all to, the degree of continuum of phi for general chain. Therefore, they consider the case for matrix which are like deterministic, so-called deterministic stochastic matrices, for which we have only one non-zero matrix per line. For example, this one is like deterministic also. This one, 2 by 2. This is one. So, like for bigger system is including the limitation matrices, the signal. Or also this one you can see. This one also. 2 by 2 matrices. These are the matrices. For bigger matrices, this class includes all the matrices and more. If the matrices are invertible, so are the matrices, otherwise, and other kind of matrices such as this one. And through this divide that they have done in that paper, they proved that using like the practice over this matrix characterizing this invariant distribution phi, they show that indeed the degree of continuum of this that is pretty negative. So completing this degree of continuum, it turns out that it's strictly negative. Therefore, here for the case, it's negative. If there is only one orbit, it's negative on R, and if there is more than one orbit, then it's strictly negative. And since it doesn't depend on n as you can see, the degree of continuum of phi n is the same. Doesn't depend on n. Therefore, the limit also doesn't depend on n, and it's strictly negative. Therefore, this class of market chains is indeed continuum given for the simple case for which we have like I will just show you directly here because there are many technical details. I will try to show it on the paper is published. This table. Here we use it. Another important result. That's also a joint work with Professor Ezekiel, Professor Lu, and myself, in which we prove the quantum multiplication equality for that generalize the classical notion. I mean the classical multiplication. I mean, we get the quantum extension of the multiplication points. And here it turns out that the property is quite useful to show mixing condition for the class of Engelmann. Here is just the definition of an Engelmann chain. And I mentioned before, here the same side. And then we write it. It's another way to define, to show that it's completely equal, so you can see it this way. Now we define here what's called the mixing condition. The state, I mean the quantum chain is said to satisfy this mixing condition if for a fixed observable A with n fixed and m also fixed, then if we take the shift sigma n capital N, and we take the limit as capital N goes to infinity, we get this asymptotic and the dependence for phi. The limit is phi of A and so phi of B. This is the mixing condition. In this work, we try to show that this class of Engelmann chain is using first model from the previous works. Now we see whether this condition is satisfied or not. We use this triple level in which we express it. This shift. So phi of A times the shift of B, typically we can take A to be any element and B also any element, but here it's enough to take the tensor product of B0, T, W, N. Then, by computing the correlation of the matrix chain, we get this form that says that E of identity tensor B for B is any field. It turns out that, since by applying this we get an element that belongs to the diagonal algebra, then by applying again the backward multiple operator, we get coefficient of the classical stochastic matrix generating the dynamic, because I just want to remember that this integral multiple operator is defined through stochastic matrix. And then by iterating then using this this market operation inequality, and then he gets this result that shows that indeed this class of thing, if the classical market chain is good in the sense that it has a unit and varied measure for which the matrix, our matrix like Pn converges to pi infinity, which is tensor 1, then also the integral market chain satisfies a similar quantum mixing condition. Also, some other results we have studied related to entangled Hilbert model. Entangled Hilbert model, in which we show that this class of quantum market chain define entangled Hilbert models, and then we define like the process as observation of entangled market chain. Entangled Hilbert model, and I will just show one of the applications after we did the work on entangled Hilbert model. Like we, in this paper, we consider it's a joint work with Professor Ezekiel Olusola. In this paper, we consider a complete model in which we consider what is known as the Faraday model. The Faraday model is this classical, Faraday model in which we have the dependency of sigma and one given sigma to this factor in the relative variable. What's really important for this model that it has important applications in physics, and what's also important is that it's exists in a homogeneous process, really process. Then we define the associated quantum market chain, which is in this case entangled, and also we define this associated entangled market chain. Then here what's really important in this construction is that it's defined as the structure of entangled market chain. Here we have a model is defined as a process for which we have a couple of systems, a hidden system and an observation system. For the hidden system, it's generated by these algebras, BH and related to the hidden system, and BON related to observation system. And then we have the HO process, the joint process is BH. I mean, using some algebra is BHN. And then we have defined the usual embeddings after we express it in this model, the classical, we embedded the classical equality into quantum. The quantum, single what's really important is that we inspired from the entangled Markov operator to define both the observation and the single one. Here is the observation entangled Markov operator. And also it's defined through this formula that expresses the dynamics of the electron at the moment. And here we give the structure theorem for the associated entangled
time for questions. If you have questions, we'd like you to identify and you can ask. Those online, if you have questions, you can write on the chat box. Yes. Any question?
I'm sorry, the same problem. Like, I cannot hear well because there is an echo when you talk.
Echo?
If I put on the chat or the phenomenon, conditioning to the past and given the present to the future of this process can be any count, including the weather, including maybe financial markets or whatever. A lot of application of this backward approach. Like when you say the backward approach, it's like information summarized about the backward approach. That can be anything. Like here, maybe I didn't give a lot of examples, but indeed, when given classical changes, have a lot of applications in several areas, including biology, finance, being and everything. So it has a really significance because it summarizes the correlation and the information of the future given the present. There's the randomness of in this case, there's also the entanglement, how to measure the mathematical behavior of this class of process. So it has a lot of importance and meaning related to the information. Okay, and look how we compare the question where the interpretation that our next case so that's the idea. Which say that basically the IJ is simply the probability of x n plus 1 equals j given x n equals I. Here is another expression. Another expression that defines instead of the IJ conditional expectation E from the algebra A n to n plus 1 into the algebra A. Okay, to give this maybe in a classical way, we see, okay, it gives since the diagonal section of quantum Markov chain gives the classical Markov chain, then all the classical distribution are included in. As the short is given by this picture. As you can see, no classical behavior to the entanglement of this class of quantum Markov chains. Say that this class, this class of quantum Markov chain is much richer than the classical one. It means this expression is not just a curiosity, a mathematical curiosity, but it really has a profound application in physical phenomena such as the quantum thing. pages you will find the quantum sums. So we don't consider it as an application of Markov rate.
He said, what is the position of invariant measure in this distribution?
Okay, I got another question, which is
What is the
the
position of invariant measure
uses more of the concept of phase class
in
equation.
quantum Markov chain?
Can we say that it relates to some reducible representation of certain ideas? Okay, for the class of this class of rate, maybe it's the fundamental case. Because here as you can see that you just consider the classical case. And for the Lie groups, actually, I don't have any idea whether quantum Markov chains can be related or not. Maybe from a cardio who can give some details
Maybe we have some
connection with the groups.
Mr. Akadi, there's a question. Professor Susi said we should contact you and maybe you can give an answer to that. This is the last question. This question that entangled measure uses more of the concept of phase class operators. Can we say that it relates to some theories of certain liquids? That is according to the section of the quantum Markov chains. Then we also have that was the invariant measure used in this theory of quantum Markov chains by his description.
But it's another question.
So he referred to you that
I got another question.
Professor Susi referred to you to address this question.
Ah,
Yes.
well,
Do you want to leave it to discussion or now? Not outside it. Okay.
the
Yes,
question,
another question.
Professor Kadi wants to respond to the question.
I understand the question. I will use the very figure. Use the figure of quantum Markov chain. That's a
point-
nice question.
the point of
And this is
entangled Markov chain
the paper I just showed
is
now.
that
Observe the mixing condition
there is no assumption
of the
of
tingle.
phase class.
And they were very clever.
The
Played
basic
a
point
role
was a remark that now,
like
many years ago,
here.
that
They were
see,
very
it's a
clever
very,
in doing. Describe here it is.
I have responded to you that Professor Akadi
This one is very
responding to the questions.
Chain.
Maybe he's not hearing you.
It describes this thing.
you said that.
Yes, he asked you to. Yes, he asked you.
I think he has kept.
He asked a question. I sent him a message.
So then you have,
Okay, minimize that.
Then,
so the question is clear.
You understand? I can remove the question?
No, I want
Bring it
the
down.
question is readable. It's not readable now. Scroll down, scroll down. Okay.
no, that's not his question now.
Explain more.
That's not the question.
Here.
Just
You scroll down or up?
down now.
This is the answer is exactly the same.
You are going page by page.
Because the answer is exactly the same. There is
This is the question.
Entangled.
no. Entangled measure don't use any trace class assumption. The important point of entangled measure is the following. In 1982, I gave the proof exactly in the first QP conference. I gave the proof that the classical symmetric random walk cannot be lifted to a unit. But then, a couple of decades after, then it was clear that if you relax then every macro chain can be lifted to an entangled quadratic without any trace class as solution. This is completely general, not only random walk. Every macro chain. Okay? So there is no assumption of the trace class in the, at least in the definition of a macro chain, you see, in the entangled macro chain. From the technical point of view, what made the big difference was a remark that a posteriori is not so difficult to prove. You can try to do this as an exercise. And the remark was the following. You know that sure multiplication between matrices is a positive operator. Okay, the entangled Markov chain were born when, with the following remark, the sure multiplication is not only possible, it is completely possible. Please try to do this as an exercise. To familiarize yourself with the notion of complete possibility. You will see that it is not such a... Once you know the result is what I said. The sure multiplication between matrices, finite dimension, is not only positive, but completely positive. And from this, what in his lecture, Professor Susi described, then a posteriori it was described that this transition expectation that you can define using the sure multiplication as a isometric implementation, not you, isometric. So this is the basic idea behind the entangled macro chain. No trace class assumption, no analytical assumption. The construction is completely general. It works for arbitrary macro chain, not even random walk assumption. Arbitrary macro chain.
Second question. How was the invariant measure used in this theory?
See, the invariant measure, we can prove that if the classical Markov chain of an if you remember Professor Ezekiel lecture, in the entangled Markov chain, you start with a single Markov chain, and a single Markov chain is, let us say, homogeneous chain, so we don't complicate our life with many indices. An homogeneous chain is uniquely determined, so classical Markov chain entangled Markov chain is stationary. We're using it. We don't need the stationarity hypothesis in the general construction, because also in the classical Markov chain, you don't need that the chain is stationary. The theory works for non-stationary chains. But if the classical chain is stationary, the entangled associated chain is also stationary. Okay?
Okay, we thank Professor Akadi for the response and yes, I didn't have a question. I don't know if we have any other question. Okay, if there are no more questions,